In the cooling outer reaches of a young solar system, at a temperature of roughly 1200 Kelvin, something is happening that no eye has ever watched and no instrument has ever directly measured. The gas that fills this place, a wide flat disk of hydrogen and helium and trace chemistries swirling around a star that has only recently ignited, is becoming for the first time too cool to keep certain molecules dissolved in its body. And where the temperature falls below that threshold, small things are beginning to precipitate out of the vapor, the way frost forms on a cold window from moisture invisible a moment before. These are carbon grains. Each one is a few hundred nanometers across. Each one is hexagonal, crystalline, perfectly ordered at its edges, a tiny lattice of carbon atoms arranged in flat sheets, bonded sideways to one another and stacked loosely above and below. They drift, almost weightless in this thinly populated region, falling very slowly toward the midplane of the disk, accumulating in silence over timescales that have no human name. The star at the center of this disk is perhaps a few million years old. Its light is still irregular, its nuclear furnace still settling into the long, steady burning that will carry it through the next few billion years. From a great distance in the infrared, the disk around this star would glow faintly at its inner edge, a ring of orange warm gas where temperatures hover near the threshold. Further out, the disk cools toward darkness. Somewhere in that darkness, the graphite flakes are falling. Nothing living exists anywhere near this place. There are no planets yet. There are no surfaces, no oceans, no atmospheres. There is only chemistry, performing itself in slow and absolute silence across a span of space wider than the current orbit of every planet in our own solar system combined. The first thing to understand about how worlds form is that they do not begin with rock. They begin with a decision. The decision is not made by anything with a mind. It is made by a number, a ratio, carried in the chemistry of the gas from which every solid thing in the system will eventually condense. That number is the ratio of carbon atoms to oxygen atoms. In our own solar system, carbon is less abundant than oxygen. That gap between them, that small numerical deficit on carbon's side, governs everything. It means that when the cooling gas begins to drop out its solid phases, silicon atoms find oxygen atoms first, bonding with them into the silicates and oxides that become Earth's crust and mantle. When oxygen is the more abundant of the two, it claims the silicon before carbon can. The planet that forms is a familiar kind of world, pale-mantled, oxygen-threaded, water-capable, geologically active in the way our Earth is geologically active. But in this other disk, the one where graphite is already falling, that ratio has gone the other way. In this disk, carbon outnumbers oxygen, not by much, perhaps, a difference that in ordinary human accounting would seem like a rounding error. But chemistry is not human accounting, and at the temperatures where solid grains condense from cooling gas, even a small numerical advantage tips the bonding hierarchy entirely. When carbon atoms are more numerous than oxygen atoms, the silicon in the cooling gas finds carbon first. Silicon carbide forms instead of silica. Graphite falls instead of olivine. The solid matter accumulating in the midplane of this disk is dark and light and chemically alien, and the planet that will eventually grow from it will be unlike anything in the solar system we know. The ratio at which this shift occurs sits near a value of about 0.8, meaning 8 carbon atoms for every 10 oxygen atoms is enough to begin pushing the chemistry toward carbon-bearing phases rather than oxygen-bearing ones. When the ratio passes 1, when carbon atoms equal and then exceed oxygen atoms, the transformation is complete. In a disk where carbon to oxygen sits above one, the silicates do not form in significant amounts. Silicon carbide takes their place. Graphite condenses freely. The entire mineralogical character of the planetary system is rewritten by this single parameter before a single pebble has accumulated. The graphite grains drifting through the midplane of such a disk are physically delicate. Graphite is one of the softer solid materials. Its layers bond strongly within each flat sheet, but only weakly to the sheets above and below, so the material shears and splits along those planes with almost no resistance. Each falling flake carries this structural character with it, this tendency toward softness, toward layered division, toward the fine dark dust that such grains make when they collide. But in the midplane of the disk, they are not colliding hard. They are drifting gently, settling like very slow snow onto the accumulated pebbles and larger bodies already gathering below. Those pebbles are themselves made of graphite and silicon carbide and traces of other carbon-bearing compounds that have condensed from the cooling gas at slightly different temperatures and slightly different temperatures and slightly different distances from the central star. They are near black, held in the hand. If hands existed here, if any human body could survive within kilometers of this place, they would feel lighter than an equivalent rock of silicate, because graphite and silicon carbide are less dense than the iron magnesium silicates that fill the Earth's mantle. A pebble of this material, about the size of a fist, would weigh somewhat less than a comparable piece of granite. The world it will eventually help to build will be less dense, gram for gram, than Earth, slightly puffed, slightly more buoyant in the gravitational arithmetic of its own mass. At a certain distance from the star, far enough that the temperature has dropped below the sublimation point of solid carbon, graphite grains can persist indefinitely. Closer in, the heat would drive them back to gas. The boundary between where graphite remains solid and where it returns to vapor is one of the invisible thresholds that shapes the geography of the entire forming system, deciding which planetesimals will be carbon-rich and which will be stripped of their most volatile carbon phases. This boundary is not a wall, it is a gradient, a gradual cooling as distance increases, a gentle dimming of the stellar heat, until at some radius the graphite locks in and does not leave. The planetesimals forming beyond this boundary accumulate over millions of years. Each collision between two carbon-rich bodies adds mass to the growing objects. Slowly, over timescales measured in tens of millions of years, in some models, the largest of these bodies grow large enough to draw in surrounding material gravitationally, their increasing mass bending the trajectories of nearby smaller bodies toward them, sweeping the disk of its loose material the way a growing snowball clears the snow beneath it. Two planetesimals forming in the same disk, at nearly the same orbital distance from the same star, can end up with dramatically different compositions if the disk's chemistry differs by even a small fraction around the critical ratio. One may accumulate pale silicate material, forsterite, instatite, the familiar gray-white minerals of rocky planets. The other may gather carbon-bearing phases almost exclusively. Their surfaces, if they could be compared side by side, would look almost nothing alike. The silicate planetesimal would be pale gray, matte, ordinary in the way that volcanic rocks and asteroid samples are ordinary, the kind of surface a geologist would recognize. The carbon planetesimal would be near black, its surface absorbing rather than reflecting, its material softer and more easily powdered, its chemistry pointing toward a class of world that has no close relative anywhere in the solar system. The critical ratio, that number sitting near 1, is not determined by anything that happens in the disk itself. It arrives there from the star. A star carries its chemical composition from its birth. The molecular cloud from which a star forms carries whatever abundance of elements the surrounding galaxy has built up over its history, through the deaths of earlier stars and the nucleosynthesis of earlier generations of nuclear burning. A star born in a region of slightly elevated carbon abundance will form a disk with elevated carbon abundance. The ratio is written into the star at formation, and it passes forward into everything the disk produces, every grain, every pebble, every planetesimal, every world. This means the nature of every planet in a system is, in a real sense, the nature of its host star deferred. The star does not choose its composition. Its composition is the outcome of where and when in the galaxy's chemical history it formed, a history that precedes it by billions of years. But that composition, carried in the proportions of atoms in the gas cloud, flows forward into the disk, then into the solid grains, then into the growing planetesimals, and finally into the fully formed worlds that circle the star for billions of years after. A planet does not decide what it is made of, it inherits it. To observe the ratio encoded in a distant star, an astronomer measures the star's spectrum, the characteristic pattern of dark absorption lines, where the star's own atoms have absorbed light at specific wavelengths before it can escape to space. Carbon and oxygen each produce their own lines at their own wavelengths. The relative depths of those lines encode the relative abundances of those two elements in the star's atmosphere, which reflects the overall chemical composition of the material from which the star and its system formed. Looking at those lines, narrow dark notches pressed into a spectrum of color, each one a few nanometers wide, each one the signature of a specific electron transition in a specific atom, is looking at the blueprint of every solid body in that system. The blueprint for a carbon world looks like a modest excess of carbon's line relative to oxygen's. It is subtle. In many surveys of stellar spectra, it would appear unremarkable. But that quiet numerical imbalance, carbon atoms fractionally more numerous than oxygen atoms in a star's atmosphere, is the full instruction set for a world unlike anything in our solar system. The darkness of the surface, the rigidity of the interior, the silence of a geology that never produces water, never permits the familiar chemistry of rock and ocean and air that Earth's silicates make possible. Graphite condenses in the temperature range between roughly 1000 and 1500 Kelvin. Within that band, the gas is cool enough for crystalline carbon to lock into its hexagonal structure, but warm enough that the surrounding gas still churns with enough energy to produce regular, well-ordered lattices rather than disordered, amorphous deposits. The graphite that forms at 1200 Kelvin in a carbon-rich disk is not the rough, powdery graphite of a pencil mark. It is crystalline, small, geometrically precise, each platelet a few hundred nanometers wide, its edges sharp, its layers stacked with the long-range order that only slow, low-energy condensation from gas can produce. These crystals drift, they fall, very slowly they accumulate. In the midplane of the disk, the thin, dense region where the gas is thickest, and where the gravity of the disk's own mass pulls material toward the flat center plane, the grains settle and stick to one another through gentle electrostatic adhesion, building loose aggregates that are mostly empty space between grains, fragile structures that would crumble at a touch. Over millions of years, the aggregates grow. The growing bodies develop enough gravity to survive collisions that would shatter smaller structures. They become pebbles, then boulders, then kilometer-scale bodies whose gravity reaches outward to collect still more material. At every stage, the carbon-to-oxygen ratio is the invisible hand that decides what each new piece of accreted material contributes. In a disk above one, almost every incoming piece is dark, carbon-bearing, graphite or carbide-rich. The growing planetesimal does not dilute its character with incoming silicate material because there is almost none to incorporate. It grows darker and denser with carbon at every scale, from the microscopic crystal to the kilometer-wide body to the eventual planet. Silicon carbide condenses alongside graphite at slightly different temperatures and slightly different positions in the disk. It is pale gray, harder than graphite by a wide margin, not as hard as the corundum or diamond that form in other geological conditions, but significantly more resistant to abrasion than the soft layered sheets of graphite. In a carbon-rich planetesimal, silicon carbide and graphite exist together, each concentrated at the depths and surface layers where their formation temperatures were met, each contributing its different character, one pale and hard, one dark and soft, to the eventual landscape of the world that forms. That world, when it finally reaches planetary scale and geology begins to organize its interior by density, will be stranger than almost anything our solar system contains. But that organization, that geology, belongs to the far future of this still forming body. For now, in the disk there is only the cooling of gas and the quiet accumulation of dark grains. The grains do not know they are the beginning of a world. The ratio does not know it governs the fate of every solid body in the system. The star at the center does not know its chemical composition is a blueprint for darkness and rigidity, extending tens of thousands of kilometers downward into a planet that will not exist for another 50 million years. None of it knows anything. The chemistry simply runs its course, determined entirely by the temperatures and the numbers, the heat of the disk at each radius, the ratio of carbon to oxygen in the gas, the condensation temperatures of each solid phase, and the outcome is as certain as a physical equation and as unhurried as geological time. It is worth pausing on the quiet completeness of this. The decision has been made in this disk without any moment of decision. The carbon to oxygen ratio arrived in the forming disk from the molecular cloud before the star ignited, before the first grain condensed, before the disk had fully settled into its flat spinning geometry. The ratio was there in the gas before the gas was a disk, carried from whatever earlier stellar generation seeded this region of the galaxy with its particular blend of elements. That seeding happened hundreds of millions of years before this star formed. Those earlier stars burned and died and scattered their material into the interstellar medium, and that material drifted and mixed, and some of it gathered under gravity to form this new molecular cloud, and in the cloud the ratio was already set. The world that will form in this disk, dark, graphite-surfaced, diamond cored without water or silicate, or the familiar mineralogy of Earth, was, in a deep sense, decided at the moment those earlier stellar generations ended. The explosion of a star that died before this solar system existed determined in part what ratio of carbon to oxygen would appear in this particular disk, and that ratio determined what kinds of grains would condense, and those grains determined what kinds of worlds would form. This is not a metaphor. It is simply the chain of physical causality running forward through time without interruption, each step following from the one before, each generation of stellar chemistry seeding the next. The darkness of a world is an inheritance, and the inheritance was written long before the world. The hexagonal graphite crystals falling through the midplane of this disk are each a tiny copy of the same geometry. Six-sided, flat, bonded at the edges to identical neighbors in the plane of each sheet, loosely connected to the sheets above and below. This geometry is not accidental. It is the natural equilibrium configuration of carbon atoms at low energy, the arrangement that minimizes internal stress, the shape that carbon prefers when it cools slowly from gas at moderate temperatures and pressures. The same geometry appears wherever graphite forms under similar conditions, in meteorites, in interstellar dust, in the deposits left by comet impacts on planetary surfaces. The hexagon is carbon's resting shape. At higher pressures, tens of thousands of times atmospheric pressure, deep inside a growing planet, the same carbon atoms rearrange into a different geometry. Instead of flat sheets loosely stacked, each carbon atom bonds to four neighbors in a tight three-dimensional lattice of tetrahedra. The material becomes diamond. The transformation is not quick. It requires enormous pressure, sustained over geological time, and it happens deep inside a body large enough and massive enough to generate those pressures from the weight of its own overlying layers. But in a carbon-rich planet, given time and mass, graphite becomes diamond at depth. The dark surface material and the transparent interior material are the same element, arranged into different geometries by the weight of the world above them. The graphite grains falling through this young disk do not yet feel that pressure. They drift in near weightlessness, each one a few hundred nanometers wide, each one a tiny flat hexagonal crystal, each one carrying within its structure the potential to eventually become part of the interior of a world where kilometers down, the same atoms will have rearranged themselves into the hardest natural solid known. But that transformation belongs to the deep future, to the completed planet, to the geological history of a world that does not yet exist. For now, the disk cools, the gas continues to thin, the grains continue to fall. At the inner edge of the stable graphite zone, the temperature hovers near the lower limit of the condensation range. Here the grains are larger, having condensed earlier when the temperature was higher, and the crystallization was slightly faster. At the outer edge, the grains are smaller, the condensation newer, the crystals more delicate and less ordered. The disk is a gradation, not a uniform sheet of identical material, but a radial spectrum of grain sizes and compositions, each radius expressing the history of temperatures that have prevailed there as the disk has cooled. The midplane is thicker toward the star, thinner further out, and the grains are not evenly distributed through its volume. They concentrate in layers, settling under the disk's own gravity toward the plane, forming thin, dense sheets of accumulated solid material that are the actual working surfaces, where planetesimal growth happens most efficiently. Between these sheets, the gas is still relatively clean. The solid material, the graphite, the silicon carbide, the traces of other condensed phases, has fallen out of the gas and concentrated in the plane. This is the nursery. This is where the dark worlds begin, not in some dramatic event, not in a collision or an explosion, but in the long, quiet falling of hexagonal crystals through a thinning gas, grain by grain, over millions of years, until enough material has settled into proximity that gravity can take over and begin the slow, patient work of building something planetary. The star at the center burns. The disk spins. The grains fall. There is no sound in this place, no atmosphere to carry pressure waves, no surface to absorb or reflect vibration. The carbon grains fall in absolute silence through a space that has been this way for millions of years and will continue this way for millions more. The timescale of planet formation is so far beyond the human sense of duration that any attempt to feel it directly dissolves into abstraction. It is better to remain with the small, with the single grain, with the hexagonal crystal, a few hundred nanometers wide, drifting through cold dark gas toward the midplane of a disk that is, in this moment, building the foundation of a world that will never see water, never feel the movement of tectonic plates, never support anything that can recognize its own carbon origin. And yet the carbon in that grain, and the carbon in the planet it will help build, and the carbon in every graphite crystal that has ever condensed in any carbon-rich disk around any star in the galaxy, is the same carbon that drifts through the bodies of every living thing that has ever existed. The same element, the same geometry, sometimes the same hexagonal ring structure that appears in graphite, appears also in the ring molecules of organic chemistry, in the carbon compounds that form the backbone of biology. That relationship is not a coincidence. Carbon forms these geometries because of how its electrons are arranged, because of the quantum mechanical fact that it has exactly 4 electrons in its outer shell, able to form exactly 4 bonds, able to sit at the center of a tetrahedral or a flat hexagonal structure with equal chemical ease. A planet built of graphite is built of the same element that built the observer. That fact does not change the planet's darkness or its rigidity or its geological silence, but it carries a quiet weight when considered slowly, in the dark, in the long middle hours of a night that will end without fanfare. The spectrum of the star at the center of this disk, if it were displayed as a band of color with dark notches pressed into it, would show the relative abundances of its elements in those notches. Carbon's notch and oxygen's notch, their depths quietly encoding the ratio that governs everything else. The notch for carbon is fractionally deeper relative to oxygen than it would be in the spectrum of our own sun, just fractionally. The difference in the spectrum is a matter of a few percent in the relative depth of 2 absorption features, each only a few nanometers wide, measured against a background of continuous color from the star's photosphere. That small difference, a few percent in the depth of 2 dark lines in a band of color produced by a distant star, is the entire origin of the dark world. The entire source of the graphite crust, and the diamond interior, and the silicon carbide outcrops, and the flat black plane that will one day stretch from horizon to horizon under a sky that receives no reflected light from the surface below. All of it follows from those 2 dark lines and their relative depths. The disk cools, the grains drift downward, the ratio persists, unchanged, in the gas, in the grains, in the growing bodies, in the eventual planet. There is a kind of determinism in this that is worth resting in, not the determinism of fate in any human sense, no intent, no purpose, no design, just the forward motion of physical causality, each step following from the one before, as reliably and as quietly as water finding its level. The chemistry of a long-dead stellar generation encoded in an interstellar gas cloud, the gas cloud collapsing under its own gravity into a new star and disk, the disk cooling, the ratio expressing itself in the condensed phases, the grains accumulating, the planets forming, and somewhere, much later, in a completely different part of the galaxy, beings made partly of carbon sitting in the dark, thinking about it. The ratio is, in the end, an invisible architectural decision. It is written into a star's chemistry before the star fully forms, carried in the gas of the molecular cloud before the cloud collapses, inherited from the scattered material of stellar deaths that happened hundreds of millions of years before this disk began to spin. By the time the disk is cool enough for graphite to condense at 1200 Kelvin, the decision has long been made. The dark world has already been chosen. The brightness or darkness of every planet in the system, whether its surface will be pale gray silicate or near black graphite, whether its mantle will be soft olivine or rigid diamond, whether its geology will be active and water-bearing or silent and crystalline. All of it is already settled in the ratio between two numbers in the chemistry of the forming star. The grains fall, the disk spins slowly, the star burns, and in the long, unhurried darkness of the midplane, the first dark pebbles of a planet that will never know sunlight from below are already beginning to gather. The surface of a carbon world does not shine. Under the light of its distant star, the plane stretches in every direction without a single bright point, without a glint, without the pale scatter that any ordinary rocky surface would throw back toward the sky. The light arrives and the surface takes it, all of it, or nearly all, absorbed into the molecular structure of compressed hexagonal carbon, converted to gentle warmth, never returned. Standing on such a plane, the sensation would not be of darkness exactly, but of a world that has decided, at the most fundamental level of its chemistry, to hold what it receives rather than give it back. The star hangs in a black sky. The ground beneath gives nothing to that sky. Between the two, there is no borrowed brightness at all. This quality of the surface has a precise name in the science of planetary light. A surface's albedo is the fraction of incident light it reflects, from 0, which reflects nothing, to 1, which reflects everything. Ice and cloud carry albedos near 0.9. The moon, pale and bright as it appears from a dark field, reflects roughly 1/10 of the sunlight that reaches it. A graphite surface carries an albedo of between 0, 0.2, and 0.05, not a 10th, not a 20th, a 50th. At most, every photon that reaches the plane has a 95 in 100 chance of being absorbed, of disappearing into the carbon lattice, and emerging again only as slow infrared heat. The surface is not darker than coal by accident. It is darker than coal because it is made of the same material that makes coal dark, laid down without the diluting presence of any paler mineral to lift it even slightly toward gray. Coal has a matte, slightly oily quality when held in the hand. A graphite plane would feel different, not oily but almost frictionless in places, with a faint tendency to smear, as graphite does, leaving a dark residue on anything pressed against it. The individual grains of the surface would be extraordinarily small, each one a microscopic platelet, a crystalline sheet, just a few hundred atoms thick, its hexagonal carbon rings bonded laterally in planes, but barely bonded at all between one plane and the next. Those weak between-plane bonds are why graphite is soft. They are why a pencil leaves a mark. On a planetary surface compressed by billions of years of its own weight, these platelets would pack tightly, each one resting on the one below, the whole assemblage friable and granular, not a solid floor so much as an immensely deep accumulation of very small, very dark pieces. Where a meteor has struck, the crater floor would be unnaturally flat. On a silicate world, impact creates glassy melt that pools and re-solidifies with irregular texture, or rock that fractures in complex three-dimensional patterns. Graphite does neither. Under the sudden pressure of an impact, the platelets compress and shear. The floor of the crater fills not with glassy stone, but with compressed sheets of carbon, stacked like pages in a book that has been pressed flat. The ejecta blanket spreading outward from the crater rim would be made of the same material, thin layered sheets of graphite flying outward through the thin air and settling across the surrounding plain. Seen from above, such a crater would look almost tidy, its margins clean, its floor dark and level, the ejecta arranged in overlapping sheets that catch no light and cast no reflection back toward the observer. Around it, the plane continues exactly as before. The atmosphere above the surface would be thin and cold and chemically strange. No water vapor would move through it, no oxygen would accumulate. Where gases had gathered at all, they would tend toward carbon-bearing molecules, carbon monoxide in the lower atmosphere, perhaps methane in trace amounts where reduced conditions allowed, perhaps small quantities of carbon dioxide where any residual oxygen had bonded away. The air would carry none of the familiar chemistry that makes the air above a silicate world a biological possibility. It would be chemically consistent with everything below it, an extension of the same elemental choice that made the surface dark, the crust hard-edged and granular, and the interior far below, something entirely different in structure and completely continuous in composition. Across such a plane, at local noon, the light would lie flat and strange. On Earth, atmospheric scattering turns the sky blue and softens even direct sunlight into something diffuse. On a world with a thin, almost transparent atmosphere and a black surface, no scattered brightness rises from below, no blue dome wraps overhead. The star, wherever it sits in the sky, would appear as a sharp, unblurred point. Its light would fall at a steep angle onto a surface too dark to reflect it, and the shadows cast by any low outcrop would be sharp and black. The horizon, where the surface meets the sky, would offer no brightness, no haze. It would simply stop, the dark ground giving way to the dark sky with only the star's position to distinguish one from the other. Along the terminator, where the warmth of the star gives way to the long cold night, thin graphite dust would drift in whatever faint wind a thin atmosphere could carry. Each grain, a microscopic hexagonal platelet, tumbling slowly end over end, settling against the base of a low ridge where pale silicon carbide outcrops in narrow bands against the black surface. These ridges would be the only thing approaching contrast on the plane. Silicon carbide, the other dominant mineral of a carbon-rich world, has a hardness far above graphite's own near-frictionless softness, and it weathers differently, breaking into angular pieces rather than into fine dust. Standing slightly proud of the graphite plane that has eroded to powder around it. Pale gray against near black, the only approximation of color that this surface would offer to any sky above it. Beneath the surface, the weight of the world presses downward through the first few 100 meters of compacted graphite, without any dramatic change. The material deepens, the pressure climbs, the temperature rises very slowly, moving away from the cold of the near surface toward the genuine heat of planetary depth. The graphite remains. Graphite for a long time, through hundreds of meters, through the first few kilometers, through tens of kilometers of increasing pressure and increasing darkness. Graphite is stable across a wide range of pressure conditions, and the phase boundary, where it gives way to something harder and more structured, lies deeper than the casual visitor to the interior might expect. The surface is graphite. The near surface is graphite. The deep near surface is graphite still. The boundary lies much farther down, at depths where the pressure has built to a level that the uppermost layers of this world could not imagine from above. At roughly 300 to 400 kilometers of depth in a world roughly as massive as Earth, the pressure reaches the threshold at which the carbon lattice can no longer maintain its layered hexagonal arrangement. The bonds between the planes of carbon atoms, already the weakest feature of the graphite structure, are overcome by the weight of everything above. The carbon atoms rearrange themselves. Each atom forms 4 bonds instead of 3, reaching out to its neighbors in a 3-dimensional tetrahedral structure rather than in flat sheets. The material that results from this rearrangement is, in the strictest mineralogical sense, the same element. Every atom is carbon. but the arrangement is entirely different, and the properties that follow from the arrangement are entirely different. The softness is gone, the darkness changes. What was opaque and layered and yielding becomes clear and hard and rigid beyond almost any other solid material in the known universe. This is the graphite to diamond transition zone, and it does not announce itself with a clean horizontal line. The transition plays out across tens of kilometers of depth, influenced by small variations in local temperature and by the trace presence of other elements mixed into the carbon. In some places, at a given depth, the transformation has already completed. In others, at the same depth nearby, patches of graphite persist a little longer, surrounded by growing regions of diamond, the two phases coexisting in an uneasy proximity that will resolve only with further pressure and further time. The transition zone is neither entirely one thing nor entirely the other. It is a gradual clarification, a slow arrival at a new structural state spread across enough depth that any single boundary drawn on a cross-section diagram would be an approximation. Inside the transition zone, the change in physical character is absolute. Graphite perpendicular to its basal planes carries heat poorly. Diamond carries heat with extraordinary efficiency, among the highest thermal conductivities of any known solid material. Graphite has a Mohs hardness of 1 to 2. Diamond has a Mohs hardness of 10, the top of the scale, defined by diamond itself, because nothing harder has ever been found to scratch it. The transition zone bridges these two extremes across its tens of kilometers of depth, a region where the planet's two dominant mineral phases exist together, and where the thermal and mechanical character of the world is still negotiating between the soft, dark past above and the rigid, transparent future below. Below the transition zone, the interior of a carbon world is diamond, in the same way that Earth's interior is broadly silicate. Not a gem, not a crystal with facets and faces. A dense, enormous aggregate of carbon atoms in the tetrahedral diamond arrangement, compressed under the weight of the world above into a rigid structure that conducts heat readily and resists deformation with an almost incomprehensible stubbornness. The diamond mantle of a carbon world with Earth's mass would extend from the base of the transition zone, 300 or 400 kilometers down, to depths of several thousand kilometers, through most of the planet's radius, through the overwhelming majority of its interior volume. The graphite crust above it, even if several dozen kilometers thick, would represent a thin skin compared to the vast diamond interior beneath. This interior is utterly dark. No light could survive at these depths, and there is no light to survive. No radioactive decay produces visible light. No chemical process generates bioluminescence. Heat moves through the diamond in the form of lattice vibrations, phonons, the mechanical equivalent of warmth spreading through a solid, invisible, silent, felt only as temperature rather than seen. The diamond does not conduct heat in the way that a metal conducts heat, through the movement of free electrons, but through the sheer efficiency of its rigid atomic lattice, passing thermal energy from atom to atom along the tetrahedral bonds with a speed that far exceeds what any silicate mineral can manage. In a world whose interior is made primarily of diamond, the heat that accumulated during planetary formation, the heat of accreting impacts, of radioactive decay, finds its way toward the surface far more readily than in a silicate world. A carbon planet dissipates its primordial heat faster than Earth did. Inside the diamond mantle, the question of movement becomes one of almost perfect stillness. Earth's mantle moves. It is solid rock, but given millions of years of time, it flows, it convects. Hot rock from depth rises slowly, cools, and sinks again, carrying heat toward the surface in a churning, centuries-slow circulation that drives the plates above, opens ocean basins, raises mountain chains, and has reshaped the surface of the planet dozens of times over its history. This convection is possible because silicate rock, even in the solid state, has a viscosity that allows very slow deformation under sustained stress. Diamond has a bulk modulus, a resistance to compression and deformation that far exceeds any silicate mineral. The diamond mantle of a carbon world is so mechanically resistant, so rigid in its three-dimensional bonded structure, that solid-state convection of the kind Earth's interior supports becomes essentially impossible. The interior does not stir, it does not slowly overturn. It conducts heat upward through the efficiency of its lattice, but it does not carry rock from depth to surface in great slow plumes, does not fracture and renew itself. It sits enormously rigid, enormously quiet, and does not move. Without a convecting mantle, the surface has no driver. On Earth, the plates move because the mantle beneath them moves. The surface is broken into pieces, and those pieces are pushed apart or drawn under by the slow engine of interior circulation. A carbon world, with its rigid, motionless diamond mantle, offers no such engine. The graphite crust above sits on a foundation that does not flow, does not generate the horizontal stresses that crack silicate crusts into plates, does not push or pull the surface through any geological cycle. The graphite plane is not a plate. It is a single continuous dark surface, compressed and layered and granular, sitting on a rigid diamond interior and going nowhere. The mountains that do not rise here, the ocean basins that do not open and close, the volcanic chains that do not appear above the subduction zones. Their absence is the silence left by an interior too rigid to drive them. In the absence of plate tectonics, the graphite surface weathers according to other forces. Meteor impacts add material and disturb the surface locally, pressing the graphite into flat-floored craters and throwing thin sheets of compressed carbon across the surrounding plain. Thermal cycling, the expansion and contraction that comes with the alternation of day and night, hot and cold, absorbed and radiated heat, stresses the near-surface layers and causes the thin platelets to fracture and separate, producing finer and finer graphite dust over long time. Any wind that a thin atmosphere could generate would lift and carry this dust in low suspension, settling it in drifts and layered deposits against the pale silicon carbide ridges and into the floors of craters that have themselves become filled with graphite sediment. The surface is changed over long time, not by volcanism or tectonics, but by the accumulation of small mechanical events, impacts, thermal stresses, the slow grinding of particles against particles, the settling of dust. If volcanic activity occurs at all on a carbon world, it would arrive differently from anything silicate volcanism produces. Silicate magma is viscous, slow-moving, produced by the partial melting of mantle rock under heat and pressure, and driven to the surface through the mechanisms that plate tectonics creates, at diverging plates, at hot spots, at subducting margins. A carbon world has none of these. But deep in the interior, where the heat has not yet fully dissipated, and where local temperature gradients push some carbon-bearing material past a melting threshold, thin, low-viscosity carbon-rich melts could form. These melts would be far less viscous than silicate magmas. They would flow rapidly, almost like a thin liquid, rather than oozing slowly, driven upward through fractures in the graphite crust by the pressure of the material above them. They would rise quickly, not over centuries, but over hours, cutting narrow channels through the graphite layers above the diamond mantle in a process that echoes, in a carbon context, the kimberlite pipes of Earth, the narrow volcanic conduits through which Earth's deepest mantle material is sometimes brought to the surface, and through which diamonds occasionally arrive from depth. On a carbon world, such a conduit would bring not diamonds to the surface from below, but a thin pulse of superheated carbon-bearing liquid to the surface, a narrow eruption, quiet compared to any silicate volcano, leaving a small vent structure surrounded by a modest spray of material. No broad lava fields, no shield volcanoes rising thousands of feet, no calderas the size of continents, a narrow pipe and a small dark eruption, and then silence again. Over geological time, as the interior cools and the thermal gradients that could produce even these modest melts diminish, the conduits seal. The last volcanic activity on a carbon world, once it ends, leaves no trace that anything ever moved in the planet's interior, no tectonic features, no recent lava flows, no active rift zones, just the graphite plain, undisturbed and dark, and the silicon carbide ridges standing in their pale contrast against it. The cooling of a carbon world follows a different curve from the cooling of a silicate one. In the first billion years, when the planet retains the heat of its formation and the diamond mantle conducts that heat upward and outward with great efficiency, the rate of heat loss is substantial. The surface is warmer than an older planet of the same mass would be, and any thin atmosphere traps some of this outward warmth. As the billions of years accumulate, the interior temperature falls. The graphite to diamond transition zone deepens slightly because the boundary between the two carbon phases is a curved line in pressure-temperature space, and as the planet cools, the pressure required to push graphite into diamond is reached at a greater depth than it was when the planet was younger and hotter. A younger, warmer carbon world has its transition zone closer to the surface. An older, colder carbon world has it slightly deeper, its diamond mantle marginally thinner, its graphite crust fractionally thicker. The mineralogy of the interior is a record of the planet's own thermal history. Several billion years into a carbon world's existence, the volcanic conduits have been cold for a long time. The transition zone has settled at its current depth and will not move significantly again. The surface has been reshaped 10,000 times by small impacts and thermal cycling and the slow drift of graphite dust, but its fundamental character has not changed since the planet first solidified. A dark, friable, granular plane of compressed hexagonal carbon absorbing the star's light, holding the heat, returning nothing to the sky. The diamond interior below has not moved. It has conducted heat and been emptied, slowly, of the warmth that once filled it. Now it sits at temperatures that, while still far above the surface, are modest compared to the great heat of the planet's first age. There is a quality to this geological stillness that has no close equivalent among worlds that move. Earth's interior is active now, will be active for perhaps another billion years before its heat budget runs too low to sustain the plate cycle. A carbon world reaches its stillness earlier, the diamond conducting its heat away faster, the rigid mantle preventing the kind of slow convection that would replenish surface heat from within. By the time geological stillness arrives on a carbon world, it is a final condition. The kimberlite-like conduits are sealed and will not reopen. The transition zone will not shift. The graphite surface will continue to accumulate meteoritic material, to be powdered by thermal cycling, to drift and settle. But these are the processes of a surface unattended by any deeper engine. The world below the surface has stopped in the only way a world can stop. Not abruptly, not dramatically, but gradually and completely, one slowing process at a time, until what remains is a rigid, transparent interior that holds its shape without effort, and a dark surface that faces the star without reflection. The star's light continues to arrive. The graphite surface continues to absorb it. The heat that enters the surface moves through the near-surface layers and is slowly radiated back as long-wavelength infrared, invisible to any eye that might be watching from above. No volcanic heat rises from below to add to it. No tectonic rearrangement warms one region more than another. The surface temperature is set primarily by the star's distance and luminosity, and by the almost total absence of any albedo to moderate it. The dark planet holds the warmth it receives in its surface layers and sends it gently back towards space. Below the graphite plane, below the transition zone, in the enormous rigid volume of diamond that constitutes most of this world's interior, the silence is absolute. Not the silence of empty space, which carries its own qualities of radiation and rare particle passage, but the silence of a material that has reached its equilibrium, an enormous crystal aggregate under immense pressure at steady temperature, bonded in 3 dimensions with such thoroughness that nothing within it needs to move or change. The phonons that carry heat through its lattice move at speeds the surface would not recognize, but they carry no sound, no vibration that propagates outward, nothing that could be felt or heard even from within the material. The diamond mantle is simply there, an enormous and crystalline fact, extending from the base of the transition zone to the deep interior of the planet, rigid and cold tending and complete, in that downward descent from the black, light-absorbing surface through the granular near surface into the compacting deep graphite across the tens of kilometers of the transition zone where graphite slowly clarifies to diamond, and then into the vast quiet of the diamond interior. There is a coherence. Every layer is the same element. Every layer is carbon, arranged differently, behaving differently, but related to the layer above and below it by the simple fact of atomic identity. The transition zone is not an intrusion of one material into another. It is the same element, discovering under pressure what else it knows how to be. And what it knows how to be, under enough pressure and over enough time, is rigid and transparent and essentially immovable, a deep interior that has spent billions of years not failing, not reforming, not eroding, simply remaining locked in its tetrahedral bonds in a darkness that has no witness and needs none. The graphite to diamond boundary, somewhere in the middle depth of such a world, is one of the quietest transitions in the geology of any known kind of planet. Above it, the dark surface absorbs a distant star. Below it, the diamond extends in an unbroken rigid volume that will outlast the graphite above it, that will outlast the star that warms the surface, that is, in a structural and material sense, among the most permanent arrangements of matter that a planet-sized body can produce. The graphite crust will be worn and reshaped by time, impact by impact, dust drift by dust drift. The diamond below will not. It has already found its form. It will keep it in the dark, under pressure, without witness, for as long as the planet itself holds together, which is to say, for a very long time yet. The surface of a carbon world does not shine. It has never shone. From a great distance, against the light of its star, it is barely visible, a dark body, slightly warmer than the surrounding space, absorbing rather than reflecting, present in the data of instruments rather than in any obvious brightness. But the darkness of the surface is only the beginning of the description. What lies beneath it, layer by layer, from the fine graphite dust of the plane, down through the compressed granular deep, through the slow transition where carbon finds its hardest form, and into the rigid, silent, enormous diamond interior. That full depth is the character of the world. Not just dark, dark at the surface, and below the surface, crystalline, soft at the surface, and below the surface, harder than anything that the surface itself could scratch, absorbing above and conducting below, moving heat upward through an interior that does not itself move, a world settled into itself long ago, and resting there still, in the dark and the pressure and the quiet, billions of kilometers from the nearest place where any of this has been imagined. Far out in the galaxy, at a distance the eye cannot hold, a star burns at the color of cooling embers. Its light does not arrive white or yellow at the edge of the disk of gas and dust that slowly turns around it. It arrives amber. It arrives deep red-orange, the color of a coal held just past its brightest moment, a color carried across 40 light-years of cold space before it touches anything solid. The star's surface runs at roughly 2,500 Kelvin, not the 6,000 Kelvin of a sun like ours, but cooler, deeper in tone, the kind of warmth that belongs to a hearth rather than a furnace. This is the light that falls on a world in the making. This is the light that carbon-rich dust has been filtering for billions of years, absorbing the blue end of the spectrum in molecular layers near the stellar surface before the radiation ever reaches open space, leaving only the long, slow wavelengths to travel outward through the dark. The disk that circles this star is not the pale, icy gray structure that surrounded the young sun. Its composition was set before the first grain of solid matter, condensed out of the cooling gas, set by a ratio, a proportion between two species of atom that was built into the star's own chemistry from the beginning. Carbon outnumbers oxygen here, not by much, not by a factor of 10 or 100, but by enough. One carbon atom for every oxygen atom, and then slightly more. In a disk like that, chemistry runs differently. Oxygen binds with silicon to form forsterite and enstatite, the pale glassy silicate minerals that make up most of the solid rock beneath a person standing on Earth, only when oxygen is abundant enough to go around. Here, it is not. Carbon claims silicon first. It claims it quietly, without drama, at temperatures between roughly 1,000 and 1,500 Kelvin, forming silicon carbide crystals no larger than a few micrometers across, and leaving almost nothing for the silicate chemistry that built every familiar mountain, every ocean floor, every continental shelf that has ever carried life. The carbon atoms that do not bond with silicon do something simpler. They bond with each other. Carbon has a quality no other element possesses in quite the same way, an easy, almost promiscuous willingness to join itself, to form rings and chains and sheets of its own atoms, stable across an enormous range of temperatures and pressures. In the cooling gas of a carbon-rich disk, at temperatures where solid grains first become possible, carbon atoms arrange themselves into flat hexagonal sheets. Each atom in the sheet bonds to three neighbors at angles of exactly 60 degrees, forming a lattice as regular as a honeycomb, and the sheet has no particular reason to stop forming at any edge. It grows, lattice unit by lattice unit, until it becomes a crystal of graphite, thin, dark, soft, and chemically specific to the conditions of its birth. These flakes settle into the midplane of the disk. They drift and accumulate, and slowly, over millions of years, they gather into the first dark pebbles of a carbon world. What is extraordinary about this process is not that it is strange, but that it is exact. The same physics that governs the chemistry of minerals in a protoplanetary disk also governs the interiors of the stars those disks surround. The carbon that settles into these flakes came from somewhere. It did not simply exist, scattered evenly across the galaxy, waiting to be incorporated into a disk. It was made in the core of a star, under temperatures that make the disk look cool by comparison. Helium nuclei fused into carbon nuclei in a reaction so specific and so dependent on an almost accidental resonance in the energy levels of carbon 12 that its discovery astonished the physicists who worked it out. Without that resonance, carbon would barely form at all. With it, carbon becomes one of the most abundant products of stellar nuclear burning. The carbon now drifting through a protoplanetary disk in hexagonal graphite flakes was, before anything, a piece of a stellar interior, something made in fire and then expelled into the cold. The stars that produce the highest carbon abundances are not young stars, they are old ones. Specifically, they are stars in a late phase of their lives, after they have exhausted the hydrogen in their cores and moved through a long, complex sequence of interior changes that eventually brings them to a state called the asymptotic giant branch. On this branch, a star has expanded to enormous size, a red giant hundreds of times the diameter it once had, and it burns helium in a thin shell surrounding an inert carbon-oxygen core, with a hydrogen-burning shell above that, and a deep convective envelope above both. The star on the asymptotic giant branch is not steady. It pulses. Its helium shell burns in periodic thermal instabilities that astronomers call thermal pulses, and each pulse drives a brief episode of deep mixing that carries material from the hot interior up into the outer layers. These mixing events are the third dredge-up, and what they carry upward is carbon-12, freshly made by the fusion of 3 helium nuclei in the helium shell, now ascending through thousands of kilometers of stellar interior into the convective envelope and eventually into the stellar atmosphere itself. The triple alpha process, by which 3 helium nuclei become a single carbon nucleus, requires temperatures above roughly 100 million Kelvin and densities high enough that helium nuclei encounter each other frequently enough for the 3-body collision to occur. 2 helium nuclei merge first into beryllium-8, which is unstable and exists for only a fraction of a second, long enough in the compressed heart of a helium-burning shell for a 3rd helium nucleus to arrive and complete the fusion before beryllium-8 dissolves. What emerges from this collision is a carbon-12 nucleus, 6 protons, 6 neutrons, bound together with enough energy to remain stable for the rest of cosmic time. In a star of roughly 1.5 to 4 times the mass of the Sun, this process repeats across many thermal pulses, and each pulse's dredge-up event deposits more carbon into the stellar envelope. The Sach/O ratio, the ratio of carbon atoms to oxygen atoms in the star's outer layers, climbs with each cycle. It passes through 1/2, through 3/4, and then, after enough pulses, it crosses unity. Carbon now outnumbers oxygen in the star's photosphere. The star has become a carbon star. The spectral change that accompanies this transformation is visible even across the light years. Before the Seti/O ratio crosses unity, the star's atmosphere is rich in oxygen-bearing molecules, titanium oxide, vanadium oxide, the molecular bands that give ordinary M-type giant stars their orange-red color. After the crossing, those molecules disappear. Oxygen is now scarce relative to carbon, and carbon-bearing molecules flood the atmosphere instead. Diatomic carbon, the molecule called C2, forms in abundance and absorbs the blue and green portions of the star's light. Cyanogen, the CN molecule, adds its own absorption bands. The molecule CH contributes further. The combined effect is a deep filter laid across the entire spectrum of a star that was already cool and already reddish, pulling it further toward amber and orange red, giving carbon stars their characteristic deep color that sets them apart from any other type of star in the night sky. Where an ordinary giant is the color of a fading sunset, a carbon star is the color of the deepest ember in a fire that has been burning for an hour. The nearest star of this kind lies roughly 430 light years away in the constellation Leo. It goes by the designation CW Leonis and also by the name IRC plus 10216, a catalog number that reflects how it was first detected, not by visible light, but by infrared emission, the deep warmth of its cool surface and its surrounding dust shell glowing at wavelengths longer than the eye can see. CW Leonis is not a small star quietly aging. It is embedded in the thickest circumstellar envelope of any carbon star known this close to the solar system, a vast, slowly expanding cocoon of gas and dust that extends far beyond the star itself, out to distances where the material has been traveling outward for hundreds of years since the stellar wind carried it away. The wind from CW Leonis blows at roughly 14 kilometers per second, slow by stellar standards, but persistent, and it has been building this envelope for a very long time. Inside that envelope, the chemistry is extraordinary. Radio astronomers and infrared observers have identified more than 80 distinct molecular species in the circumstellar envelope of CW Leonis, making it the richest natural chemical laboratory in the nearby galaxy. Hydrogen cyanide forms in abundance. Acetylene drifts through the expanding shell. Long carbon chain molecules, species that would be unstable in ordinary chemistry, persist in the cold outer envelope, where ultraviolet radiation is shielded by the dust, and where the densities are low enough that reactions occur slowly. And among all of these molecules, embedded in the dust as solid particles rather than gas phase molecules, are silicon carbide grains, small, crystalline, a few micrometers across, each one formed in the hot inner envelope close to the stellar surface and then carried outward by the wind. Silicon carbide is transparent to visible light, but absorbs and emits infrared radiation at a wavelength of 11.3 micrometers, a characteristic feature that appears in the infrared spectrum of CW Leonis as a single smooth peak rising above the background emission of the dust. It is a quiet signal, narrow and specific, but it is unmistakable. Silicon carbide grains, the same mineral that dominates the outer layers of the carbon worlds forming around carbon-rich stars, are here, now drifting through the envelope of a carbon star, 430 light-years away, and being detected by instruments on Earth. The grains that form in a stellar wind do not stay in the wind forever. The envelope expands and cools. The outer regions of the shell eventually merge with the surrounding interstellar medium, and the grains, the silicon carbide crystals, the graphite flakes, the carbon chain molecules, frozen into ices in the cold outer shell, join the general reservoir of interstellar dust. In molecular clouds, this dust collects and compresses when a cloud collapses under gravity to form a new stellar system. The carbon-rich dust from a previous generation of carbon stars can be incorporated into the new disk. The 6/O ratio of the new disk reflects, in part, the chemical history of the material from which it formed, the nucleosynthesis of stars that lived and died long before the new system began. Carbon stars, in this sense, are factories. They make carbon in their interiors, carry it to their surfaces through dredge-up events, expel it into space in their winds, and seed future protoplanetary disks with the raw material for carbon worlds. The carbon flakes settling into the midplane of a distant disk are, in many cases, the processed output of asymptotic giant branch stars that burned out billions of years ago. The mass range that produces carbon stars, roughly 1.5 to 4 solar masses, encompasses a very large number of the stars in the galaxy. Stars like the Sun, slightly above average in mass, are candidates for the carbon star phase late in their lives. The Sun itself may not reach the full carbon star stage, since dredge-up efficiency depends on mass in ways that place the Sun near the lower boundary of the relevant range, but stars a bit more massive than the Sun certainly do. This means that carbon stars are not rare exotic objects at the outer edges of stellar classification. They are a common phase in the life of a common type of star, one that billions of the galaxy's stars will pass through or have already passed through since the first generation of stellar nucleosynthesis began enriching the interstellar medium. The carbon-rich dust that now drifts through the galaxy, the silicon carbide grains embedded in interstellar clouds, the molecular material detected in circumstellar envelopes, all of it is cumulative, the sum of billions of years of carbon production by stars that spent their final productive phase pouring carbon out into space. When a carbon star finishes the asymptotic giant branch phase, it does not simply stop. Its envelope is gradually shed through the stellar wind until what remains is the hot, dense core, a white dwarf composed mostly of carbon and oxygen, no longer fusing any elements, simply cooling over billions of years. White dwarfs cool slowly and steadily, and most of them do so without any further chemistry being added to their surfaces. But some white dwarfs, a fraction of the population, show something unexpected in their spectral lines. Their photospheres, the thin outermost layer from which light escapes, contain traces of elements that should not be there. Silicon, calcium, iron, carbon-bearing material. These elements are heavier than hydrogen and helium, and in the intense gravitational field of a white dwarf, they should sink out of the photosphere and into the interior in a matter of days or centuries. Their presence means they are being continuously supplied by something falling in. The best explanation, and the one that fits the evidence from hundreds of observed white dwarfs, is that solid bodies, asteroids, planetesimals, the remnants of planetary systems, are being perturbed inward by gravitational interactions disrupted by the white dwarf's tidal forces and accreted onto its surface. In some polluted white dwarfs, the mix of elements settling into the photosphere suggests the disrupted body was a rocky planet or a large asteroid rich in silicon carbide, the mineral signature of a carbon-rich planetary system. The white dwarf's photosphere becomes, in this way, a record of the solid bodies that orbited a star through its entire main sequence and giant branch life, and then, at the very end, fell into the cooling remnant. There is something very still about that image. A star that spent billions of years on the main sequence, then swelled to a giant, then shed its outer layers in a slow expanding shell of carbon-rich gas and dust, and now rests as a cooling white dwarf, its photosphere gently contaminated by traces of silicon carbide, accreted from the broken remains of worlds that formed in the carbon-rich disk it once had. The nuclear fire is gone. The stellar wind has long since dispersed. What remains is a dense, quiet object, roughly the size of a planet, with a surface temperature slowly dropping toward the temperature of empty space on a timescale measured in billions of years. And still, faintly, it carries a chemical record of everything that came before. The carbon made in the triple alpha reaction, the dredge-up events that carried it to the surface, the grains that condensed in the wind, the planetesimals that formed in the disk, now dissolved and accreted, and written into the spectrum of the remnant as quiet absorption lines at specific wavelengths. The observations of polluted white dwarfs are carried out using spectrographs on large telescopes. The technique is not dramatic in its execution. An astronomer points the telescope at a point of light that is a white dwarf, collects its spectrum over an exposure of perhaps an hour, and then examines the resulting spread of wavelengths for the small, narrow absorption features that indicate contamination. The features are not loud. They are slight dips in the continuum at positions corresponding to the spectral lines of silicon or carbon or other elements. In many cases, the contaminating abundances are only a few parts per million of the white dwarf's photospheric mass. But the technique is sensitive and the signal is real, and what it reveals is that planetary bodies or their remains are a common feature of stellar evolution across a wide range of stellar types and chemical environments. The carbon star's journey from a hydrogen-burning star on the main sequence to a carbon AGB giant to a cooling white dwarf takes, depending on its mass, somewhere between a few 100 million and a few billion years. For the planetary system forming around it, this timescale is long enough to allow solid bodies to grow from dust grains to planetesimals to planets of significant mass, long enough for the planetary architecture to develop its own gravitational dynamics, long enough for moons to form and orbits to migrate and resonances to establish themselves. The carbon world that might form around a carbon star does not appear in the same geological moment as the carbon star's AGB phase. The planet forms during the star's main sequence youth, when the disk is still present, when temperatures in the disk midplane are appropriate for solid condensation. The star's carbon-rich chemistry is already built in at that point, carried in the initial composition of the stellar nebula. The AGB phase comes later, after the planet has long since formed and settled into its orbit. And when the expanding stellar envelope finally sheds and the white dwarf appears, the carbon worlds of that system, dark, rigid, possibly cold, may continue to orbit the cooling remnant for billions of years more. Around CW Leonis itself, no confirmed planetary system has been detected. The star is too deeply embedded in its own circumstellar envelope to be examined with the precision needed to detect planets. Its dust shell scatters and absorbs light at the wavelengths where planet detection techniques operate, and the irregular pulsations of the star create radial velocity variations that would mask the subtle signatures of planetary companions. But the presence of more than 80 molecular species in the envelope, the confirmed detection of silicon carbide grains, and the star's position as the most chemically characterized carbon star in the nearby galaxy make it the closest available laboratory for understanding what carbon-rich planetary chemistry looks like in practice, even if the specific planetary population of CW Leonis remains out of reach. The silicon carbide grains in the envelope drift outward from the star at a few kilometers per second. At that speed, a grain departing from close to the stellar surface would reach the outer edge of the visible envelope in roughly a few thousand years. Some of those grains will continue outward indefinitely, joining the interstellar medium and drifting through space for millions or billions of years before finding their way into a collapsing molecular cloud. Others will be destroyed by ultraviolet photons from neighboring stars. A small fraction may fall back toward the stellar remnant after the envelope disperses, accreted in the slow rain of material that eventually contributes to white dwarf photospheric contamination. Each grain is a few micrometers across, smaller than the diameter of a human hair by a factor of 10 or 20, and each one formed in the hot inner wind of the star at temperatures of 1,000 Kelvin or more, crystallizing into a specific arrangement of silicon and carbon atoms as the wind cooled, carrying that crystal structure intact through the expanding envelope and out into space. The structure of each grain is the direct record of the conditions under which it formed: the temperature at the formation site, the density of the gas, the ratio of carbon to silicon in the local chemistry. In meteorites that have fallen to Earth, grains of silicon carbide with isotopic compositions that identify them as having formed in carbon star winds have been found preserved in the oldest, most pristine meteoritic material. These are presolar grains, particles that predate the sun's formation, that were incorporated into the solar nebula when the molecular cloud collapsed, and that survived the formation of the solar system intact inside rocky meteorite parent bodies. The solar system is not a carbon-rich system. Its E/O ratio is well below 1. Its rocky planets are silicate worlds, and its bulk chemistry reflects an oxygen-dominated disk. But even here, in a silicate planetary system built from oxygen-rich material, there are carbon star grains locked inside the most ancient meteorites, remnants of stars that burned and died before the sun existed. In a carbon-rich system, those presolar grains would not be rare inclusions in otherwise silicate material. They would be the dominant solid phase. The silicon carbide that forms in interstellar space as a trace component would be the rock. The graphite that appears in Earth's geology in small veins and deposits, an industrial material, a mineral of limited geological significance, would be the crust of every solid world. The chemistry that produces a few exotic grains in the meteoritic record of a silicate system would be the universal chemistry of an entire planetary system, repeated across every body from the innermost rocky world to the outermost planetesimal in the cold disk. This is what it means to form in a carbon-rich disk around a star whose chemistry began differently, not a modification of familiar planetary formation, not a silicate world with carbon added, but a completely separate branch of planetary chemistry that produces a completely different kind of solid world. The carbon star and its disk represent an alternative beginning. The triple alpha reaction, the dredge-up events, the molecular filters that strip blue light from the stellar emission, the silicon carbide grains drifting through the circumstellar envelope, these are not curiosities appended to the standard model of planetary formation. They are the beginning of a different model, one in which the ratio of two atomic species determines not just the mineralogy of a planet's crust, but the entire character of every solid body in a system, from the chemistry of its interior to the darkness of its surface to the rigidity of its geology. The deep amber light of a carbon star falling on a disk where carbon exceeds oxygen is the beginning of all of it. The red-orange glow of CW Leonis is detectable from Earth using equipment that fits inside a small observatory. A medium-sized telescope, a sensitive infrared detector, and a patient observer can resolve the brightness of this star against the background of the night sky. What cannot be seen, what no instrument currently deployed is capable of resolving at this distance, is the detailed structure of the grains inside the envelope. They are too small and too embedded in the surrounding emission. But the 11.3 micrometer feature in the infrared spectrum, that single smooth peak in the emission from the circumstellar dust, carries their signature unmistakably. It rises above the continuous warm glow of the dust at a wavelength that corresponds to the vibrational frequency of the silicon-carbon bond in the crystal lattice of silicon carbide, a frequency set by the masses of the silicon and carbon atoms and the stiffness of the bond between them. The peak is not sharp like a laser line. It is broad and smooth, a gentle hill in the spectrum, because the grains are not all identical. They vary slightly in size and temperature and composition, and their combined emission blurs the sharp molecular resonance into a rounded feature. But its center is always at 11.3 micrometers, always silicon carbide. The measurement requires no direct observation of the grains themselves. The physical chemistry of the silicon-carbon bond speaks for itself across 430 light-years of space, arriving at the telescope as a quiet infrared excess at one specific wavelength, telling the observer what the grains are made of without anyone having ever touched one. The stars that produce carbon worlds, the grains that form in their winds, the envelopes through which those grains travel, the white dwarf remnants that accrete the broken remnants of carbon-rich planetary systems, all of this forms a single chain of events spread across billions of years and tens of light years. The chain is not hypothetical. Its links are observable at every stage. Carbon-12 nuclei form in helium-burning shells and are carried upward by dredge-up events. This is measured in stellar spectroscopy. Carbon stars are identified and cataloged across the galaxy by their deep red color and their molecular absorption bands. Thousands of them are known. The circumstellar envelope of CW Leonis has been mapped in detail at many wavelengths, and the silicon carbide grains in it have been detected and characterized. Polluted white dwarfs are observed and their photospheric contamination analyzed, revealing the elemental compositions of disrupted planetary bodies. Presolar silicon carbide grains from carbon star winds are extracted from meteorites in terrestrial laboratories, and their isotopic compositions measured with mass spectrometers. Each step in the chain is real and measured and placed on the same physical foundation. What remains less directly observed is the carbon world at the end of the chain, the planet that formed in the carbon-rich disk of a main sequence carbon star progenitor, dark with graphite, rigid with the transition to diamond at depth, its crust soft and its interior motionless, and its surface absorbing rather than reflecting the deep amber light it receives. But the absence of direct observation does not make the planet uncertain in any deep sense. Its existence follows from chemistry that is well understood, from disk conditions that have been modeled in detail, from mineralogy that can be calculated from first principles given the composition of the condensing gas. The carbon world is not a speculation appended to a body of solid evidence. It is the expected output of a process that is measured and understood at every other stage. The silicon carbide grains in the envelope of CW Leonis drift outward in their slow wind at a few kilometers per second. In the cold quiet of the outer envelope, where the dust temperature has dropped to a few hundred Kelvin and the gas density is thin enough that molecules can persist for long periods without colliding, each grain moves in a slow, straight path away from the star that made it. It has no trajectory toward any specific destination. It carries only its crystal structure, its infrared emission feature, its chemical identity as a product of carbon-rich stellar chemistry. And that identity, small, silent, chemically specific, drifting through the dark, is readable from Earth in the steady glow of a spectrum at a wavelength that no human eye can see, but that instruments can measure without difficulty. A quiet signal from a distant star, confirming that the building blocks of carbon worlds are present, observable, and real. At roughly 300 kilometers below the surface of a carbon world, in absolute darkness and under pressure that would reduce any familiar rock to powder, graphite gives way to something else. The change is not a line. It is not a wall or a seam where one thing ends and another begins. Across tens of kilometers of depth, the flat hexagonal sheets of graphite stacked loosely on top of one another and held only by the gentlest of chemical forces, begin to buckle under the weight of everything above them. Carbon atom by carbon atom, the geometry shifts. The bonds that once ran sideways across a plane reorient, reaching up and down as well, locking each atom into a rigid three-dimensional cage. The soft, dark mineral of the surface is becoming something else entirely. Quietly, in the dark, under no influence other than weight and time. That new thing is diamond. The transition happens across a depth range of perhaps 40 or 50 kilometers, a gradual and intimate geological transformation occurring in a place that no instrument has reached and no light has ever entered. At the top of this zone, the rock is mostly still graphite, but its layers are compressed and beginning to deform. A little deeper, the first diamond crystals appear, tiny and scattered among the graphite, the way frost first appears on a cold surface before it spreads. Deeper still, the graphite becomes the minority, then the trace, and then it is gone, and what remains is a mineral whose properties are almost the opposite of what lay above it. Graphite and diamond share exactly the same atoms, carbon, only carbon in both. But the way those atoms arrange themselves changes everything about how the material behaves, how it feels, how it moves heat, and what it costs a planet to cool down. The graphite above is a conductor of heat, only poorly, its layered planes trapping thermal energy between sheets, passing it upward slowly, reluctantly. The diamond below conducts heat with an efficiency that has almost no parallel in the natural world of minerals. Heat moves through diamond the way sound moves through dense solid, faster, more completely, more willingly than through almost any other substance. The thermal conductivity of diamond runs somewhere between 1,000 and 2,200 watts per meter Kelvin, depending on crystal purity and the orientation of the measurement. That number carries weight when placed beside silicate rock, which manages somewhere between 3 and 5 watts per meter Kelvin in Earth's mantle. Diamond does not merely conduct heat better, it conducts heat at a scale that changes the entire thermal history of a planet. Where Earth's silicate mantle holds its primordial heat for billions of years, releasing it slowly through convection and volcanic output, and the slow creep of warm rock toward the surface, a diamond mantle would move the same heat upward with almost indecent efficiency, draining the interior the way a cold metal surface drains warmth from a hand placed flat against it. The interior of a diamond is not the faceted, glittering object of a jeweler's display. Under the conditions prevailing deep inside a carbon world, diamond exists as an aggregate, a compressed and interlocking mass of crystals jammed against each other under pressures that hold every grain in place. There is no light here to catch and scatter. There is no geometry to admire from outside. What exists in every direction for thousands of kilometers in the more massive configurations of carbon planets is a material of extraordinary rigidity, moving heat with a speed and completeness that slowly empties the planet of the energy it was born with. The models published to characterize these interiors suggest that in a carbon-rich planet carrying roughly the same mass as Earth, the diamond layer might extend from around 300 to 400 kilometers depth down through most of the planet's radius. In larger bodies 2 or 3 times Earth's mass, the diamond layer dominates by volume so completely that the graphite crust above it is comparatively thin, not unlike the skin of a fruit over a hard pit, a layer of softness over a core of extraordinary density and rigidity. The graphite crust, dark and friable, sits at the top of a structure that grows harder and harder with each kilometer of depth. The transition from loosely bonded graphite sheets to diamond crystal aggregate, playing out in that gradual, unhurried conversion zone somewhere between 300 and 400 kilometers down. There is something important about that conversion zone that the simple image of a sharp boundary obscures. The line where graphite becomes diamond is not fixed. It is not drawn once and held forever. In pressure-temperature space, the graphite to diamond boundary traces a curved path, not a horizontal threshold. A planet that is hot, young, still full of primordial heat, still radiating warmly from within, carries its graphite diamond boundary deeper than a planet of the same mass that is cooled. Heat expands the range over which graphite is stable. As the planet cools, the boundary migrates upward through the interior, slowly converting what was once warm, borderline graphite into the first diamond crystals, adding new material to the diamond zone year by year over geological time. This means the interior of a carbon world is not static. Over billions of years, the diamond zone grows. The conversion front rises. A planet that began with a relatively shallow diamond layer because its interior was hot and the graphite stability field extended deep, slowly shifts toward one in which diamond has claimed most of the volume. The planet is changing from the inside, quietly, without any eruption or surface sign, just the slow crystallographic conversion of one carbon phase into another, driven by a planetary interior losing its heat to space far faster than Earth ever could, guided upward through the diamond layer below. The rigidity of diamond brings a second consequence, one that shapes the entire geological character of a carbon world from its first billion years onward. On Earth, the silicate mantle is stiff, but not so stiff that it cannot flow. Given enough time and heat, the olivine-dominated rock of Earth's deep mantle creeps slowly, convecting in great slow loops that carry warm material up from the depths and drag cool material back down. This convection is the engine of plate tectonics. It is what opens ocean floors and closes them again, what lifts mountain ranges and wears them down, what cycles carbon and water and sulfur between the surface and the deep interior in the long chemical exchanges that keep Earth's surface active across geological time. Diamond's bulk modulus is far higher than that of silicate minerals. The bulk modulus is a measure of how much a material resists compression, a proxy for stiffness, and diamond's stiffness in this sense is enormous compared to olivine or pyroxene. Solid-state creep, the slow flow of crystalline rock under sustained pressure and heat, becomes dramatically slower when the material is diamond rather than silicate. The deep interior of a carbon world, rather than convecting in the slow, productive loops that sustain Earth's geological engine, would be nearly motionless. The diamond mantle would sit still. It would conduct heat upward through thermal diffusion, moving energy without moving mass, the way a copper rod conducts warmth from one end to the other, without any part of the rod physically traveling. This stillness has profound consequences. Without convection in the mantle, there is no driving force for plate tectonics. The carbon world's crust does not divide into moving sections. The surface does not refresh itself through the creation and destruction of new crust. There are no trenches where old rock descends, no ridges where fresh material wells up from below, no volcanic arcs above subduction zones, no cycle of mountain building and erosion driven by the geometry of colliding plates. The surface of a carbon world is geologically locked, not merely old, but frozen into a single configuration, its graphite crust sitting atop a diamond mantle that has no intention of moving because its material will not permit movement on any geological timescale. The planet's heat escapes upward through that diamond mantle by conduction alone, a process that is efficient in terms of moving energy, but passive in terms of moving mass. The diamond does not need to flow in order to carry heat, and it carries heat the way light carries energy, by transmission, not transport. So the interior of a carbon world cools, but it does so without the geological dynamics that make a silicate world like Earth recognizable as active and alive. It cools from the inside out, the diamond layer growing as the boundary migrates, the planet's internal temperature dropping over geological time until the conversion front has risen nearly to the crust, and the remaining heat is a faint residue of what was present at the planet's birth. If volcanic activity were to occur on a carbon world, it would look nothing like what happens on Earth. On Earth, volcanic eruptions are driven by silicate magma, molten rock that forms when the mantle melts, partially under reduced pressure or elevated temperature, rising buoyantly through the crust and erupting at the surface as lava. The magma is viscous, thick with silicate chains, and its behavior at the surface is determined largely by that viscosity and by its dissolved gas content. Carbon worlds have none of this silicate chemistry. What they have under conditions where the interior does melt is something closer to a carbon-rich fluid, a liquid that behaves very differently from silicate melt. The carbonate and carbon melts that might form in a carbon world's interior would be extraordinarily low in viscosity, thin and mobile compared to any silicate magma. Where silicate lava flows slowly and thickly across a surface, constrained by its own resistance to flow, a carbon melt would move through a fracture system in hours rather than years. The most likely pathway for such a melt would be through narrow vertical conduits, cracks that propagate upward from the mantle through the graphite crust, driven by the buoyancy of the low-density melt against the denser crystal rock around it. On Earth, these kinds of conduits exist. They are called kimberlite pipes, and they are the channels through which diamonds reach the surface of our silicate world, carried upward in rapid, low-viscosity pulses from deep mantle conditions. A kimberlite-style eruption on Earth is not a slow volcanic event. The material moves upward through the crust quickly, propelled by dissolved volatiles and the low viscosity of the carbonate melt, and it arrives at the surface carrying with it material from depths that other volcanic processes never reach. On Earth, the diamonds that end up in jewelry were transported this way, ripped from their high-pressure home in the mantle, and carried upward faster than equilibrium chemistry could convert them back to graphite, preserved in the low-viscosity melt as it ascended, and then cooled at the surface. On a carbon world, this process would run in a different chemical context, but with the same basic mechanics. The fracture propagates upward from the region where melt has formed, and the low-viscosity carbon fluid, carrying fragments of the diamond mantle in suspension, ascends through the graphite crust in a matter of hours. At the surface, the fluid spreads out over a small area, cools rapidly, and deposits its cargo as a dark field of carbon minerals, graphite and diamond fragments, mixed in a solidified matrix, the mark of the one geological process capable of bringing material from deep inside a carbon world briefly to its surface. These events would be local and intermittent. They would not reshape the surface the way sustained volcanic activity reshapes a silicate world. There are no shield volcanoes built up slowly over millions of years as lava pours from a single long-lived hotspot. There are no calderas collapsing over depleted magma chambers. There is a fracture and a rapid ascent and a small dark field of deposited carbon, and then the fracture seals and the surface returns to its long graphite stillness. The kimberlite-like vent is not a landform in the conventional sense. It is more like a scar, a small and subtle mark left by the one violent moment in an otherwise motionless geological history. The graphite crust itself, sitting atop this rigid diamond mantle and occasionally pierced by these narrow conduits, has its own particular character. Graphite at the surface of a planet is not graphite as encountered in a laboratory on Earth, a pure, orderly crystal measured and tested at room temperature. Planetary surface graphite would be a compressed aggregate of flakes and grains, impure, mixed with silicon carbide in many regions, fractured by impacts and thermal cycling and the slow stress of a crust that sits without moving on a mantle that does not support it dynamically. The layered structure of graphite, those hexagonal planes held together only by weak van der Waals forces, makes the surface material prone to shearing along those planes, prone to granular breakdown, to the production of fine dark dust, to the slow accumulation of loose graphite particulates in low areas and around the bases of any raised features. An impact event on this surface would not produce the same kind of crater as an impact on silicate rock. Rock under impact can melt, flow, splash, and vitrify, become glass in the moment of impact's heat, and then freeze into the complex shapes of an impact melt sheet, the raised rim, the central peak. Graphite under impact would behave differently. At the temperatures produced by impact, graphite can vaporize or convert partially to diamond, but the very softness of the surface material absorbs the energy differently than hard silicate rock. The crater floor would be unnaturally flat, its ejecta blanket not of glassy melt, but of compressed carbon sheets and fine graphite dust, fanning outward across the dark plane in a pattern that carries no reflected light back to any observer above. Over a very long time, impact ejecta accumulates. Fine graphite dust from repeated smaller impacts, thin compressed sheets of carbon material laid down over the original surface, a slow blanketing of the terrain under a sediment of its own pulverized crust. The surface of an old carbon world might be covered in a layer of this fine dark material, and huer live of live spores wet, and would perforbingen tivard, and huer leachest by sport, loosely packed and easily disturbed, sitting over the compressed graphite of the original crust. The whole thing a record of every collision the planet has experienced since its formation, written in carbon, in the dark, in layers too thin for any individual stratum to distinguish. The thermal discontinuity between the graphite crust and the diamond mantle below adds another layer of strangeness to this interior picture. Graphite is a poor conductor of heat, perpendicular to its basal planes. The same layered structure that makes it so soft and shear-prone also impedes the flow of heat in the direction perpendicular to the layers, which in a planetary crust means impeding the flow of heat upward toward the surface. Diamond, below, conducts heat with exceptional efficiency in all directions. At the boundary between these two carbon phases, there is a dramatic change in thermal properties. Heat arriving from below, carried upward by the efficient diamond, meets the relatively resistive graphite above, and must work harder to cross that boundary. The result is a thermal bottleneck at the crust mantle boundary, a thin zone where the efficiency of the deep interior's heat transport meets the relatively poor efficiency of the surface layer. Heat accumulates slightly at this boundary, not to the point of melting or dramatic consequence, but enough to establish a steeper temperature gradient through the graphite crust than through the diamond mantle below. The crust runs slightly hotter relative to what its depth might predict than a simple linear extrapolation from the surface would suggest. The boundary is not dramatic or dangerous. It is simply a consequence of asking two very different carbon phases to exchange heat across their interface, each operating under entirely different physical rules. Below that boundary, In the vast and quiet diamond interior, the temperature varies slowly with depth, declining over geological time as the efficient diamond conducts the planet's primordial heat toward the surface and outward to space. A young carbon world, still warm from its accretion and the decay of radioactive elements inherited from the disk material, would glow faintly in the infrared, not visibly, not to naked observation, but detectable to an instrument designed to see long wavelength radiation. The diamond layer conducts that heat steadily outward. Across the first billion years, the flux would decline measurably. Across several billion years, it would drop to a near imperceptible level, and the planet's interior temperature would settle toward a slow, steady state, far cooler than Earth's mantle temperature at equivalent depth. A carbon world several billion years old would be, in its interior, a place of extraordinary stillness. The diamond mantle, no longer warm enough to sustain the conditions for melt formation anywhere in the deep interior, would hold its crystalline structure without change. The kimberlite-style conduits that may have opened in the planet's warmer youth would have long since sealed. The graphite crust above, undisturbed for billions of years, except by the slow rain of smaller impactors, would have settled into a flat and featureless plain of dark compressed carbon, its surface recording impacts and the slow accumulation of fine graphite dust across a geological timescale so long that any individual event becomes lost in the averaging. There is a kind of permanence in this that has no clear equivalent on Earth. Earth's surface is perpetually remade, not quickly, not dramatically on human timescales, but over the long run, nothing persists. The Atlantic Ocean is geologically young. The Himalayas are a temporary wrinkle in a crust that will one day be reabsorbed and reformed elsewhere. The oldest rocks on Earth are rare survivals, exceptions to a process of continuous recycling that reaches down into the mantle and returns material transformed. Nothing about Earth's surface is truly permanent on planetary timescales. On a carbon world, the surface is not recycled. There is no mechanism to take the graphite of the crust and carry it down into a mantle that would process and return it, changed. The surface that formed in the first billion years is still the surface. It is older than anything on Earth's surface by a large margin. The graphite that condensed from the cooling disk, that accumulated into the first dark planetesimals, that compacted into the crust of the newly formed planet, that same graphite, compressed by the weight above it, and perhaps slightly reordered by the impacts of a heavy bombardment period, remains in place. It has not moved. It has not been altered. It is simply there, dark and still, as it has been since the planet was young. The thermal conductivity that stripped the interior of its heat so efficiently is in this way also the cause of the surface's permanence. Because the diamond mantle drained its heat quickly and completely, the mantle never had the energy budget to sustain long-term convection. And because convection never operated, the surface was never refreshed. The planet cooled fast and froze early. What it became in the first few 100 million years is what it remains now, billions of years later, held in its crystalline configuration by a mantle too rigid to convect and a crust too stable to recycle. In the great pressure of the deep interior, where the diamond layer is thickest and the temperature lowest relative to what early models predicted for a warm young planet, the crystals are locked together with a completeness that leaves no room for internal movement of any kind. The material is not under stress in the usual sense. It is simply compressed, every crystal face in contact with its neighbor, the whole aggregate held together by the pressure of the planet's own gravity, pressing inward from all directions. There is no flow here, no creep, no slow deformation over millions of years. There is only the crystal and the pressure and the weight of everything above. The cooling curve of such a planet, if rendered as an image rather than a graph, would look like a darkening. In the first 100 million years, the planet radiates a warmth that an infrared instrument at close range could easily detect, not glowing visibly, not lava world hot, but warm enough to distinguish its thermal emission from the background. Over the next billion years, the emission declines, not in sudden steps, but in a smooth, continuous falling. By 2 billion years, the planet is cooler than Earth at equivalent age. By 4 billion years, the interior has approached a near equilibrium with the surface temperature, the diamond mantle having done its work of conducting the primordial heat upward with such efficiency that almost nothing remains stored at depth. The planet is not dead in any dramatic sense. It simply completed the process of geological cooling at a pace that left its surface intact and its interior motionless long before Earth reached a comparable state. Earth still maintains a partially molten outer core. Earth still convects its mantle. Earth still builds and destroys its crust in the slow churning of plate tectonics. A carbon world of comparable age has already arrived at the end of all of that, not violently, not through any catastrophe, but through the simple consequence of having an interior that conducted heat too well to sustain the temperature gradients that drive geological activity. The deep interior, in this final state, holds a record of everything the planet ever was. The graphite diamond boundary, now migrated close to the surface after billions of years of the conversion front rising through the interior, marks the depth at which the planet was, early in its history, warm enough to maintain graphite stability. The diamond below that boundary began converting from graphite in the first few 100 million years, when the interior was still warm enough to maintain the conditions for the transition. Layer by layer, as the planet cooled, the conversion front moved upward, leaving behind a growing column of diamond that now constitutes most of the planet's interior volume. That diamond is a geological clock. In a sense, its depth records the thermal history of the planet, the rate at which it cooled, the efficiency with which the diamond itself facilitated its own domain's expansion by conducting away the heat that kept graphite stable. No seismometer has ever been placed on a carbon world. No instrument has measured the speed of sound through a diamond mantle or recorded the elastic waves moving through that rigid crystalline interior in the aftermath of an impact. What is known comes from models, from the equations describing the behavior of carbon at high pressure and temperature, from the measured thermal and mechanical properties of diamond and graphite in laboratory conditions at much smaller scales, from the physics of planetary interiors applied to a composition very different from Earth's, but under the same gravitational and thermal laws. The models are well grounded. The physics is not in serious dispute, but the interior of a carbon world is, for now, a place known only through inference and calculation, a vast and crystalline darkness described in equations and not yet heard as seismic waves. There is something in that situation that is not a loss. The inference is confident. The physics that predicts a diamond mantle several thousand kilometers thick in a carbon-rich planet of Earth's mass is the same physics that describes the properties of diamond in a laboratory, the same equations that govern pressure and temperature in planetary interiors generally. The carbon world is not a speculation in the sense of being a wish or an extrapolation beyond the known. It is a prediction, a specific physically grounded consequence of a different starting composition, following the same laws as everything else. The darkness of the interior is not an ignorance of the physics, but simply the inaccessibility of the place, and the place will be what the physics says it will be, whether or not an instrument ever reaches it. The graphite surface, dark and flat, sits above all of this in the open starlight, or in what passes for starlight, the dim amber-red radiation of a carbon-rich host star filtered through a thin atmosphere, falling on a surface that returns almost none of it to the sky. The surface absorbs, the interior conducts. The conversion front sits at its final depth, stable now, the planet's cooling essentially complete. The kimberlite-like conduits that may have formed in the warmer past are sealed. The graphite dust has settled into its long drifts against the low outcrops of silicon carbide. The craters are old and flat-floored, their ejecta blanketed now under the slow accumulation of still more fine dark material from impacts spread across billions of years. The diamond mantle below all of this is motionless and cold, by the standards of planetary interiors, cold in the way that a deep room in old stone is cold, not the cold of space, but the cold of something that has given up its warmth steadily over a very long time and has arrived at the temperature around it. Heat no longer flows through it in any meaningful quantity. The temperature gradient that once drove its efficient thermal transport has flattened to nearly nothing. The planet and its interior are, for most practical purposes, at a thermal equilibrium that will persist for longer than the remaining lifespan of the star above it. Somewhere between 300 and 400 kilometers below the surface, the graphite diamond boundary sits in its final position, still technically a zone rather than a line, still technically a region of mixed mineralogy, but now essentially stable. The conversion front that once moved upward through the interior year by year, having slowed to the point where it will not shift again in any geologically meaningful time. Above it, the graphite crust holds its dark, layered configuration under the weight of everything that rests on it. Below it, the diamond mantle extends downward for thousands of kilometers in absolute rigidity and darkness, a crystalline interior that has not moved and will not move, holding its atoms in their locked three-dimensional cages under the quiet and immense authority of the planet's own gravity, pressing in from all sides. The planet does not know it is finished. There is no knowing here, no awareness of the geological stillness that has descended over its interior, no recognition of what it was or what it has become. There is only the material, and the pressure, and the weight, and the faint residual warmth of a cooling that is nearly done, and the long dark surface above it all, absorbing the light that falls on it, and returning nothing back to the sky. It has been this way for longer than there have been creatures on Earth to name it. It will continue this way after the star above it has dimmed and changed and moved through its own long evolution. The graphite and the diamond are not waiting for anything. They are simply there, locked in their distinct geometries, separated by a boundary that took millions of years to reach its current position, held in place by physics that has no interest in variation or change. The planet is not dead. It was never alive. It is something else, a form of matter organized at planetary scale by gravity and chemistry and time, crystalline and cold and complete, resting in its own enormous stillness under a sky that does not reflect in any surface below it. A corundum world, imagined at rest beside a carbon world, holds the light between them in two entirely different ways. One surface is pale, nearly white, with a faint cold blue where its aluminum oxide crust catches the angle of a distant star. The other surface holds nothing. It returns nothing. Gamai Dai Han, against the pale planet, it appears less like a world and more like an absence in the shape of one, a sphere of absolute matte darkness, its boundary visible only because the stars behind it are not. These two worlds may have formed in the same disk, around the same star, from material that differed in chemistry by a fraction too small to name in any measurement a human hand could make. And yet one became a mirror and the other became a shadow, and between them the whole range of what a rocky world can be begins to open. The corundum world's crust, where it meets the thin, cold air above it, is nearly as hard as anything solid can be. Aluminum oxide, compressed and crystallized across millions of years of planetary cooling, achieves a hardness on the mineral scale that only diamond itself can exceed. Walking across it, if the word walking could apply to such a place, would produce no impression, no mark, no disturbed grain. The surface would not yield at all. It would ring faintly underfoot like the floor of a vast kiln, dry and cold and close-grained, pale enough in certain lights to seem almost luminous. No water has ever touched it. No organic chemistry has ever tried itself against it. It has been exactly this hard, exactly this pale, exactly this still, for longer than the earth has existed. Against that imagined paleness, the graphite world beside it seems almost liquid in its darkness. The albedo of its surface, the fraction of incoming light it reflects back to space, sits between 2 and 5 in every 100 photons that reach it. The rest are absorbed. On the corundum world, most of the star's light bounces back into space, and the surface stays cooler than its orbital distance alone would suggest. On the graphite world, almost everything that arrives stays. The surface drinks the radiation in. At local noon on a carbon world with a sun-like star, the surface temperature climbs, not because the rock is warm in any ordinary sense, but because it has held nearly every photon the star has offered it all morning, and the accumulated energy has nowhere to go but down into the crust, or up into whatever thin atmosphere may hang above. The corundum world and the carbon world have almost nothing in common with each other, despite their shared origin in depleted oxygen chemistry. One is pale and impenetrably hard. The other is dark, and at the surface, surprisingly soft, graphite sitting at the lowest end of the hardness scale, crumbling under the lightest mechanical pressure into fine hexagonal platelets that drift and resettle like dark snow. They formed under conditions that a single number separates, the ratio of carbon atoms to oxygen atoms in the disk that built them. If that ratio rose just past the threshold between one kind of depletion and another, produced not a sapphire hard pale world, but this soft, light-swallowing one. The same shortage of oxygen expressed in two slightly different proportions, and the outcome could not be more different in surface character, in color, in the way each world interacts with the star it orbits. Place an iron world in that same imagined array, a dense gravity-heavy body whose iron fraction approaches 70 parts in 100 by mass, and the comparison deepens further. Mercury, in our own solar system, carries an iron core disproportionately large for its size, its silicate mantle thin and dark-toned, its surface pocked with craters and etched with scarps, where the core's slow contraction has crumpled the crust from within. Now imagine a planet where that iron dominance extends far beyond Mercury's proportion. The density of such a body, walking a scale where Earth sits at around 5.5 grams per cubic centimeter, would climb well past that. It would be a small, extraordinarily heavy world, its surface a dark brownish gray under stellar light, its gravity pulling with disproportionate strength for its apparent size. From a distance, it would look unremarkable. Only its mass, measured through the gravitational tug it exerts on its star, would betray how much iron it packs inside its modest radius. The graphite world beside that iron planet would be lighter than its size suggests. Graphite and silicon carbide, The minerals that fill a carbon world from crust to deep mantle are both less dense than the iron magnesium silicates and metallic iron that pack an Earth mass planet's interior. A carbon world of Earth's mass would be slightly larger in radius than Earth, its lower density minerals spreading the same mass across a wider volume. A pure iron world of Earth's mass would be noticeably smaller, its higher density interior packed tight. These two kinds of worlds, one puffed slightly, one compressed, would look deceptively similar from space, but a careful measurement of radius against mass would place them in entirely different categories. The ratio of how heavy something is to how much space it takes up is often the first quiet fact that tells an observer what a distant world is made of. And then, the lava worlds, Corit 7 being a rocky planet in an orbit so close to its star that a single year there lasts less than a single day on Earth, holds its day side in permanent exposure to radiation intense enough to maintain surface temperatures above 2,000 degrees. At those temperatures, silicate rock does not just warm, it flows. The day side of such a planet is a broad, slow ocean of molten mineral, its surface bright and shifting, its thin atmosphere filled not with nitrogen and oxygen, but with the vapor of silicon monoxide and magnesium and iron that the heat has boiled directly off the surface. The night side receives none of that radiation and is dramatically cooler. Somewhere near the terminator, the line where day meets night, those mineral vapors condense back into solid particles and fall as a fine mineral rain onto the cooler hemisphere, a precipitation not of water, but of rock, cycling endlessly between the two sides, as long as the star burns and the orbit holds. A carbon world placed in the same extreme orbit would not produce the same result. Graphite does not melt into a flowing liquid at atmospheric pressure. Under the heat of a close stellar orbit, if the surface reached the temperature at which solid carbon can no longer hold its structure, graphite would sublime. It would pass directly from solid to vapor without becoming liquid at all. The surface of such a world would not flow like the silicate lava world's ocean. Instead, its hottest points would slowly erode into carbon vapor, thin wisps of it rising and drifting toward the cooler regions of the planet, where the vapor would cool and redeposit as a fine dark frost of carbon along the terminator and the night side. It would be a quieter process than flowing lava, less dramatic in the visual sense, a surface diminishing at its warmest edge and rebuilding at its coldest, in a slow cycle of sublimation and redeposition, hour by hour, for as long as the orbit held. The lava world glows. The carbon world, even in that extreme situation, would remain dark. Its surface temperatures, even near sublimation, do not produce visible light. The lava world announces itself. An observer with the right instrument and a long baseline orbit measurement could detect a thermal emission of a day side hotter than a blast furnace. The carbon world would absorb nearly everything and radiate it back in infrared wavelengths, quieter, harder to distinguish from ordinary rock at first glance, revealing itself most clearly not through heat but through absence, the absence of reflected light, the absence of water vapor in its atmosphere, the absence of the spectral fingerprints that a silicate world, even a hot one, carries in its thin mineral haze. This is the central challenge of finding carbon worlds from Earth, or from any instrument placed in orbit around the Sun. A silicate planet and a carbon planet at the same orbital distance around similar stars can appear nearly identical in the first measurements taken of them. Their radii may be similar. Their masses, if the carbon world is slightly larger for the same mass, diverge only a little. The The first clear distinction comes when an instrument can measure the starlight that passes through the planet's atmosphere during a transit, that thin strip of gas at the planet's edge, each molecule in it absorbing particular wavelengths of the star's light as the planet crosses in front of the stellar disk. For a silicate world with an outgassed atmosphere, that spectrum carries the broad, soft absorptions of water vapor, the sharp notch of carbon dioxide around 4.5 micrometers, perhaps the signature of oxygen if life has had time to work on it. For a carbon world, the spectrum is different at its core. The water feature is absent or nearly so. Carbon monoxide leaves its mark around 4 7/10 micrometers. Methane, if temperatures are low enough, adds its own distinctive structure. The absence of water, combined with the presence of carbon-bearing gases and no carbon dioxide, traces a chemical outline that an instrument like the James Webb Space Telescope could, in principle, detect for the right planetary target at the right orbital configuration. No confirmed carbon world has yet been found. The best candidates are planets whose measured bulk densities fall below what silicate or iron compositions would predict, combined with stars whose spectra suggest elevated carbon to oxygen ratios in their photospheres. The inference is indirect. The steps between a stellar spectrum and the composition of a planet's surface run through thermodynamics and disk physics and atmospheric chemistry, and each step carries its own uncertainty. The picture that emerges is not confirmed, but consistent enough that the question of how many carbon worlds exist in the Milky Way is a real and open one rather than a purely theoretical one. The Milky Way holds somewhere between 200 billion and 400 billion stars. Of those, a small but tungo fraction are evolved enough and carbon enriched enough to have once hosted disks with carbon to oxygen ratios above the threshold where carbon minerals dominate over silicates. Around some fraction of those stars, planets formed before the star aged past the point of supporting stable orbits. Around some fraction of those planets, conditions stayed stable long enough for planetary geology to develop and cool. The chain of fractions is long, and each step reduces the count, but even a small fraction of 200 billion is a large number. The galaxy almost certainly contains dark diamond-cored worlds, many of them distributed through the disk in a pattern no single telescope has yet traced, each one absorbing nearly all the light its star sends to it, each one sitting in geological stillness over an interior of compressed crystalline carbon, each one utterly silent, utterly lightless, unreachable, and real. An iron world, if it could speak through the only language available to it, the language of gravity and density, and the wavelengths of light it absorbs, would say something blunt and dense and compact. A lava world speaks in heat and glowing mineral vapor and a constant ancient slow flow. A corundum world speaks in hardness and pale reflected light, and the spectral silence of a surface that has nothing to exchange with its atmosphere. A carbon world speaks in absence. It speaks in the light that does not return, in the wavelengths of starlight that enter its surface and do not leave, in the atmospheric spectrum from which the water feature is missing, in the bulk density that sits lower than silicates would predict. It is a world that announces itself by what it lacks rather than what it offers. That quality, the announcement through absence, is not a failure of the world or of the instrument trying to read it. It is simply what carbon worlds are, dark by nature, quiet by chemistry, defined most clearly by the space left where silicate geology would otherwise be. 3,000 kilometers deep inside such a world, in a region where no light has ever reached, and where the pressure has been building since the first planetesimals accreted in the early disk, the diamond layer presses outward in every direction without urgency, without motion, without warmth. It formed long ago during the planet's first few 100 million years, when the interior was still hot enough to allow slow convection in the then softer deep mantle. That convection ended when the diamond's extraordinary thermal conductivity drained the primordial heat into space faster than the interior could regenerate it. The cooling ran on geological time, a billion years, then another, and the diamond that had been slowly, sluggishly mobile became still. The kimberlite-like conduits that once allowed carbon melt to rise through fractures in the crust sealed themselves as the temperatures dropped. The surface graphite, already soft and dark and undisturbed, stopped being disturbed even by the faint internal tremors that deep cooling had once produced. And then the world simply was what it had always been building toward, a dark, crystalline, rigid thing under a faint and distant star, absorbing its light without comment, sending back almost nothing, sitting in the same silence it has always held. That silence is not emptiness in any ordinary sense. Every cubic centimeter of the graphite crust holds trillions of hexagonally ordered carbon atoms, each locked into sheets that slide against one another with almost no resistance. Each sheet a perfect plane of bonded carbon, repeating across a distance the eye could not distinguish from infinity at this scale. Beneath the crust, in the transition zone where pressure has been rising for billions of years, the hexagonal sheets have given way gradually to the tetrahedral bonds of diamond, each carbon atom now gripping four neighbors instead of layering over them, the structure becoming isotropic and immovable, dense with chemical energy stored in bonds that almost nothing in the natural universe can break. The silence in that layer is the silence of a bond that has never been asked to break, of atoms that have been in exactly this arrangement since the first 100 million years of the planet's existence, and will remain so until the star above them reaches the end of its own life and changes the conditions irreversibly. That is a long time to hold still. The diamond has been holding still since before the first multicellular life appeared on Earth. When light from the distant star falls on the graphite surface, when it arrives after traveling years, or tens of years, or hundreds of years across the cold of interstellar space, it meets a surface that is the quietest receiver in the planetary taxonomy. The corundum world sends most of it back. The iron world reflects its own flat, brownish fraction. The lava world transforms it into heat and re-radiates it upward through a shimmering column of mineral vapor. The graphite world absorbs it gently, completely, the way a deep fabric absorbs sound. The photons arrive and do not leave again as light. They become thermal energy, dispersed slowly through the graphite crust, conducted poorly through the basal planes, held near the surface, warming the dark rock by a few degrees in the long day, and releasing it again into the cold night. The exchange is so quiet it barely registers from space. The planet sits in its orbit, dark and unhurried, gathering light and holding it and releasing it again, in a cycle as old as its orbit, as regular as the orbit, as uneventful as anything in the galaxy can be. There is a kind of peace in that regularity that the other worlds in this imagined array do not quite share. The lava world is violent in a sustained, geological sense, its surface never still, its atmosphere never settled, its day-night temperature gradient driving a constant mineral weather system that erodes and redeposits the surface in perpetual motion. The iron world is dense and inert, but its density carries a certain heaviness that is not quietude, so much as compression. The corundum world is still, certainly, but its high reflectivity gives it a kind of brightness that is not restful. It interacts with its star too actively, bouncing light in too many directions, its surface too crystalline and hard for the imagination to settle into. The carbon world is different. Its surface gives under the lightest pressure into soft, dark powder. Its color is the color of rest itself. Its albedo means the star's light arrives and is simply taken, quietly, without drama, without reflection. The planet does not argue with the light that falls on it. It receives it and is still. This is the deepest description of what carbon worlds are. Not a catalog of minerals, not a sequence of phase transitions, not a temperature and pressure diagram, but a certain quality of receiving without reflecting, of holding without returning, of existing in a dark and compressed stillness that has nothing to do with absence of activity and everything to do with the character of the chemistry that made the world. Carbon, in its graphite form, is among the most light-absorbing solids that nature produces. Carbon, in its diamond form, is among the most thermally efficient conductors that nature produces. A world made primarily of these two phases of a single element is a world that both receives energy readily and distributes it efficiently, absorbing at the surface and conducting through the deep interior, all in a near-perfect silence that the other worlds of its type do not achieve. The four worlds held in imagination side by side, dark graphite, pale corundum, heavy iron, glowing lava, are not the full range of what rocky worlds can be. They are 4 points on a space that has more dimensions than can be easily mapped. The chemistry of disk formation varies with the age of the galaxy, with the orbital radius of the disk, with the history of nucleosynthesis in the region of the galaxy where the star formed, with the migration of planets after their formation, with the presence or absence of giant planets in the outer system, deflecting carbonaceous material inward or keeping it away. The actual distribution of planetary chemistries across the Milky Way is a map that no one has yet drawn with any confidence. The best available data, bulk densities from transit measurements, atmospheric detections from transmission spectroscopy, stellar spectral surveys, trace only the nearest and most favorable cases. The rest are inferred from theory, from disk chemistry models, from the rare cases where a destroyed planet has left its chemical fingerprint in the atmosphere of the white dwarf star it once orbited. Those white dwarfs are among the quietest archives in the galaxy. A white dwarf is the cooling remnant of a star that once lived and burned for billions of years, and in its current state it is essentially done, a dense, slowly dimming sphere of carbon and oxygen held up against its own gravity by quantum pressure rather than heat, its surface temperature dropping by a few thousand degrees per billion years, its cooling a process that outlasts almost everything else in the stellar neighborhood. When a white dwarf that once passed through a carbon-rich phase of stellar evolution shows traces of foreign material in its atmosphere, silicon, carbon compounds, the signature of a body that once orbited it and was eventually disrupted and accreted, those traces are a kind of record. They say that a planet or a planetesimal once existed around this star. They say that the chemistry of that body was not purely silicate. They say quietly that the world-building process in carbon-rich systems can produce solid objects that persist for billions of years and carry their chemical character all the way to the end. The carbon world is one possible outcome of that process. Not the only outcome. A carbon-rich disk can produce silicon carbide planetesimals that never grow to planetary size, or carbon-rich planets that migrate into their star and are destroyed, or carbon-enriched atmospheres that escape before the planet can retain them. But in the cases where conditions favor it, where a carbon-to-oxygen ratio above unity is maintained across a disk of sufficient mass at distances where solid carbon can stay stable, What forms is this? A dark, quiet world, its surface a matte near black of compressed hexagonal carbon sheets, its interior transitioning through tens of kilometers of mixed phase into an unbroken volume of diamond that extends for thousands of kilometers in every direction. Its geological history effectively ended billions of years ago when the interior cooled and the last conduit sealed and the last tremor passed through the graphite crust and was absorbed, like everything else, without reflection, far out across the disk of the galaxy, distributed through the spiral arms at distances from their stars that place them in conditions roughly analogous to the inner planets of our own system. Some of those worlds exist right now. They exist in the same moment that this narration is spoken and heard. They are absorbing the light of their stars. They are holding their diamond interiors in the same motionless rigidity they have held for billions of years. No instrument currently in operation has resolved them clearly enough to confirm their chemistry. Their presence is inferred from disk models, from stellar spectra, from the thermodynamic logic of what happens when the carbon to oxygen ratio tips past unity in a region of gas and dust that is cold enough for solid carbon to survive. The inference is careful and consistent and supported by the pieces of evidence that are available. It is not yet confirmed in the way that a direct atmospheric measurement would confirm it. But the logic of chemistry is patient. The worlds do not need to be found to exist. The galaxy itself is patient in this way. It formed stars for 10 billion years before our sun ignited, and it will form stars for tens of billions of years after our sun has cooled to a white dwarf and faded to temperatures too low to detect from any reasonable distance. In those future billions of years, stars with carbon-enriched envelopes will age through their asymptotic giant branch phases, dredging their synthesized carbon up from the helium-burning shell into the stellar atmosphere, enriching the material they eventually shed into the interstellar medium. New disks will form in that enriched material. New planets will condense from it. New graphite worlds, dark and rigid and absorbing, will complete their formation and cool their interiors and sit in geological finality around stars no human generation will ever observe. This is not a projection made with certainty. It is what the physics and chemistry of stellar evolution and planet formation placed together imply. The universe makes the conditions for carbon worlds, and the conditions persist, and the worlds form wherever the conditions are met. That is all. It is enough. A single photon arriving at the surface of a carbon world after traveling years through space does not know what kind of surface it is approaching. It does not distinguish between the graphite grain that will absorb it and the silicate grain on an Earth-type world that might scatter it upward again. It simply arrives at the speed of light after years of unimpeded travel through the cold between stars and meets the surface. On Earth, a photon meeting silicate sand or ocean water has many outcomes. It may scatter, reflect, refract, stimulate a photochemical reaction in a molecule of seawater or a grain of quartz or a chlorophyll-bearing cell. On the graphite world, the outcome is simpler. The photon meets the surface and stops. Its energy transfers into the carbon lattice. A tiny vibration propagates outward through the bonded hexagonal sheet, dissipating in fractions of a second as heat, and the surface is, for that fraction of a second, imperceptibly warmer. Then, the energy conducts on, slowly, into the deeper graphite, and the surface returns to what it was, dark and still, awaiting the next photon and the one after that, as it has awaited them for billions of years. The star above such a world rises slowly, as stars always do on worlds with slow rotations and long days. Its light falls on the matte dark surface and is taken, no glint returns to space. No brightening of the sky above the horizon as the star climbs. The surface contributes nothing to the ambient brightness, holds no scattered light to fill the lower sky, offers no reflected radiance to the bottom of the atmosphere. The sky above a graphite world surface at local noon might be lit from above by the direct stellar disk, but from below, the surface returns nothing. It is as though the world beneath the sky is not there at all, a region of pure absence beginning at the surface and extending downward through the crust, through the transition zone, through the thousands of kilometers of still diamond at the core, down to whatever iron or carbide or exotic phase sits at the very center, where pressures exceed anything that forms naturally in Earth's interior, and the temperature, though far below the values of the early solar system, still exceeds anything a human body could approach. And yet the world is there. It is as real as any silicate planet, as complete in its geology as any world that has cooled from formation through activity into stillness. Its surface may be soft and dark and undifferentiated for thousands of miles in every direction. Its atmosphere may be thin and dominated by carbon-bearing gases with no water and no oxygen. Its sky may be the deep, unscattered color of space seen through a thin veil of gas with no blue, no clouds, no brightness below. But the world is there. It has been there for billions of years. It will be there for billions more. It is made of the same element that fills the cores of every living cell on Earth, the same element that forms the backbone of every organic molecule, the same element that the sun will one day, in 5 billion years, in its own asymptotic giant branch phase, dredge from its helium-burning shell and carry upward into its envelope and shed into the interstellar medium for the next generation of disks to incorporate. The carbon in the graphite world and the carbon in a living body share the same nucleosynthetic origin. They share the triple alpha process that fused 3 helium nuclei into 1 carbon nucleus in the heart of a star that lived and died before the sun existed. This is what it means to say that the universe makes these worlds, not as a decision, not as a purpose, but as a consequence of how matter behaves under the conditions that stars create. The conditions arise, and the chemistry follows, and the planets form, and the carbon worlds sit in their orbits, dark and still, absorbing light, waiting for nothing, needing no witness to persist. The imagined gallery of worlds, graphite, corundum, iron, lava, is a gallery that exists in space, each type formed from the same basic materials, the same hydrogen and helium, and the metals scattered through the interstellar medium by previous generations of stellar death.